Okay, hello everybody. So, welcome to the lecture today from Nuclear Engineering, Public Policy 285C, Nuclear Technology and Policy. We have had a slight change of the agenda. Bruce Tarter was to have given us a talk today on the U.S. Stockpile Stewardship Program, which is the paradigm in the post 1992 cessation of above ground nuclear testing de facto, which the U.S. and Russia, the Russian Federation, have observed. It was how the United States keeps its nuclear weapons arsenal safe and reliable in the absence of nuclear testing. Bruce himself was actually the deputy or the deputy associate director for physics. He actually played, I think was hired me effectively when I left the faculty at Stanford University in 1985, and later himself became the lab director at Lawrence Livermore National Lab. He was the director from 1994 to 2002 and played a significant role working with Dr. Victor Rees, a very brilliant man and visionary, a very astute politician. He was the Deputy Secretary of Energy responsible for the nuclear weapons program on how to pivot almost overnight on how the three labs, Lawrence Livermore National Lab, Los Alamos National Lab, Sandia National Lab, and the whole complex would continue to be supported at approximately the same budget to keep the U.S. nuclear arsenal safe and reliable and modernized in the absence of testing. And this was quite an achievement because there were a lot of pressures at the time. This was the Clinton administration to cash in on what they call the peace dividend, to effectively redirect large sectors of the DoD funding and the Department of Energy funding for domestic purposes. Other people thought that this was premature to think we would be saying goodbye forever to nuclear weapons. And in fact, as things have proven out, it's the kind of thing that one, in fact, can never quite seem to rid ourselves of. In any case, this is a program which relies on experimental facilities and experimental data to inform high-performance computing codes that can do kind of stem to stern simulations now in high fidelity of the performance of nuclear weapons or failure modes of nuclear weapons that rolls up many, many different types of physics. There's material science, there's hydrodynamics, there is explosives, there is radiation transport, atomic opacities, lots and lots and lots of very, very complex things and as the analogy has often been made about stockpile stewardship, the weapons in the stockpile were designed to have a shelf life of perhaps 10 to 12 years because from the 1950s until the 1990s, we were designing and then validating by testing new weapon systems and rolling them out on sort of a 10-year timescale for the different platforms they served, whether it would be a cruise missile, a land-based ballistic missile, submarine-launched ballistic missile, gravity bomb, or whatnot. And duration or shelf life was an issue that was not even in question, wasn't even in anybody's mind. Post-testing, we now countenance the possibility that we would be relying on a stockpile that at some point would be 20, 30, 40, 50 years old, literally 50 years old or more. And the issue is lots of things were quite unknown. How does plutonium age, for example, after when it undergoes over many, many years, the alpha decay there, which creates helium bubbles, which changes the metallurgical properties of plutonium when one tries to crush it in a primary. Lots and lots and lots of questions like that. Okay, so anyway, Bruce is of the age where he was, I think, wisely unwilling to make the trek here to appear in front of the video, and his computer technology at home did not seem to support in a robust way the Zoom technology. So what we agreed is that we would reconvene with Bruce at a later time, and that I would tidy up 3 topics which I didn't quite get to complete before we got into a more steady stream of our distinguished lecturers. So what I'm going to do here, and by the way, I see Professor Nacht is on the line as well. So at any point he should pop in and take over the mic and make his own comments as well. If you have questions or comments, please use the chat box here. I've got it open. And now, the moment of truth, I'm actually going to start up PowerPoint and then share my screen. And what I want to do first is go back and tidy up. Okay, I'm going to share the screen. Right, okay. I am going to now share, and I'm now going to go to full screen. Oops. Okay. Okay. I see people are still on the line. Can someone, Austin, can you see me? Can you see the slides?
Yep, you look good.
Okay, away we go. All right, we did most everything we intended to do before, and you've done one problem set on a little bit of a toy or a little bit of a simplified model for calculating the generation time based on cross sections and density for a Trinity type or a Hiroshima type gun type uranium assembly. And we also talked about 2-stage weapons, and the most detail you got about that was this movie we saw about the IV Mike test, the world's first thermonuclear test done in the South Pacific, a local time, November 1st, 1952, 10.6 megatons. It was a wet bomb, i.e. something that was not feasible to weaponize. It was a very, very, very large tank of liquid deuterium. It was a pure deuterium secondary. So it was a kind of a scientific demonstration, not even really an engineering demonstration, and certainly not something that was portable or mobile, but it did work. And let's see here. Okay, so let me pick up a couple of things. There's the calculation you did. Anyway, just a comment here about how life has changed. I show you this photograph here. It was actually in the newspaper. I mean, it's by today's standards, I think it would almost be inconceivable we did this kind of thing. But you know, people going to vacation down in Las Vegas to take in a show or gamble or something like that routinely got an additional bonus spectacle while they were down there. It's only about 60 miles away, 65 miles away from the Nevada test site. So pre-1962, when the US still did all its testing above ground, and after we no longer did tests in the South Pacific, we were doing them above ground in the Nevada test site, literally 65 miles away. And from time to time in Las Vegas, you would feel a very small earthquake, sort of like a magnitude 4 earthquake, and then you'd see this plume go up. And in fact, at the time, this was the height of the Cold War. There was, I think most people looked at this with patriotic approval. They were, when the next shot was going to take place was actually published in the newspaper. And as you can see here, the next test is scheduled for June 27th. And it's by today's standards, I mean, when simply could not believe that such a thing happened, took place. But that was the epoch that we lived in back then. Okay. Again, just for, I would say, for cultural benefit, I will put up this 20-page document, now declassified by Edward Teller and Stanislaus Ulam, the Polish mathematician, who conceived of the radiation-driven two-stage weapon. In its redacted form, you'll see about 18 pages, which are basically where they took a black highlighter and lined out literally everything, leaving only about 2 pages of text. And on the basis of the 2 pages of text, you could not tell whether you were looking at the instructions of a washing machine or a thermonuclear weapon. But it's risible as it is. I'll put it up there for cultural benefits. We talked a little bit about the Ivy Mike shot. Let me just show a brief YouTube here as well. Because the Soviets actually, although their first thermonuclear test was done after hours, they actually did have, make a weaponizable dry bomb. And we did our first one in 1954, March the 1st, 1954. It was called Castle Bravo. And the idea here is that one does not need to carry cryogenic liquids around, liquid deuterium, or certainly not lithium, liquid tritium in large quantities, which would have been unfeasible to make. But the idea is that once one gets the reaction going, neutrons, if one uses enriched lithium-6, that the N-alpha reaction, neutron N alpha out on lithium-6, produces an alpha particle in tritium, and therefore one can make the tritium on the fly. Lithium is a very abundant material, and literally in nanoseconds, one can go from lithium to cracking the lithium to make tritium, which is then immediately available for the fusion reaction. Now, there are many YouTube videos about Castle Bravo, and the thing about it is that the predicted yield was 6 megatons. But it actually ran away to 15. And the reason for that was that, in fact, fast neutrons, not only the slow neutrons, fast neutrons can, it turns out we're not using an inventory of pure lithium-6. I think there was something like 20 or 40% of the lithium was lithium-6. But it turns out fast neutrons can crack lithium-7, and then prime alpha T, in which case you would now have sort of 2.5 times more tritium than one would get just reckoning on the basis of the lithium-6. The cross sections were poorly known. I think these people knew that, in fact, you could crack lithium-7 to make tritium as well. But the cross sections were so poorly known that it was not appreciated what the yield of this weapon should be. And even the scientists that were in a very hardened bunker at some very large distance, and I forget how many miles, but it was very, very far away, the shock wave for that actually cracked the several feet thick of steel reinforced concrete. The cloud drifted over them, and they had to get out in a hurry, and actually had to be lifted out by helicopter, and then were sequestered on a ship where they were basically quarantined in one little hold in the ship for a very long period of time. They washed down and themselves, I think, were mildly sickened. It also caused a problem there because the cloud, the weather prediction was not accurate. The weather changed, and the cloud ended up extending a very, very, very far distance, and ended up affecting the Marshall Island natives. Even to this day, the U.S. government is still doing assessment studies after even the remediation. They're still doing follow-up studies of the effects of the radiation, looking for remnant contamination there. And what certainly did not stand the U.S. well was the fact that there was a Japanese fishing boat some 10 miles away, or maybe even further away, it might have been 15 or 20 miles away, that they were unaware. They thought they had swept the area, but there was a fishing boat there, and the fallout from there sickened the crew. And in fact, one of the fishermen died. And of course, this did not sit well with the Japanese, who just some years before, now just 9 years before, had, of course, been, the first casualties of atomic war there, and this, I think, took a long time to get over. But in any case, let me click on the link here. And
work on high-yield hydrogen bombs had progressed from Operation Ivy, culminating in the spring of 1954 with Castle Bravo.
I think you should be able to hear it as well.
The largest device ever detonated in atmospheric testing by the United States. Bravo was a hydrogen bomb using solid thermonuclear fuel, confirming the designs of Edward Teller and Stan Ulam, and paving the way to producing aircraft deliverable hydrogen bombs and more effective weapons. significantly exceeding its expected yield by 2.5 times. Castle Bravo, with an explosive power of 15 megatons, stripped islands clean of vegetation and took the scientists by surprise. The huge explosion released large quantities of radioactive debris into the atmosphere. This resulted in the exposure and contamination of some servicemen, natives, and the crew of a Japanese fishing boat, which had gone unnoticed in the security zone around the blast. This incident pushed the dangers of fallout from nuclear weapons clearly into the public mind.
Okay, so let's see. Let's see. All right, here we are. Okay, final slide from this particular slide set. I wanted to show you a slide I didn't get to show you afterwards. This is Mark Mills. He was not the first chairman of the nuclear engineering program at Berkeley, but he, in a sense, began the nuclear engineering program there, again, with the assistance and the encouragement of Edward Teller. There he is. This is a picture taken. He's giving a congressional briefing. In fact, as you can see, he's giving kind of a NE 285C type class to congressional staffers. He's talking there on some basics of nuclear physics, the nucleus, beta decay, gamma decay, timescales, and so forth. He, like many people of that time, Edward Teller himself was still an academic. Hans Mark, while they were teaching at Berkeley, also were working in the program at Lawrence Livermore National Lab. He actually died in a helicopter crash as part of the preparations for a test shot down in the Enewetak Atoll there at a very young age. The first chairman was a person, or the nuclear engineers in the department was Tom Pigford, very famous nuclear engineer, one of the pioneers. And there was Don Olander, nuclear materials guy. Then Ken Fowler, former Livermore scientist, head of the fusion program at Livermore, still comes around the department. There was Bill Kastenberg, who comes around periodically, retired up in Oregon. There was then Per Peterson for 5 years, Jasmina Vujic for 5 years, Per for a couple of years, myself, and now Peter Hostman. But Mark Mills was the head of it. Oh, by the way, I forgot. In between Tom Pigford and Don Olander was Hans Mark. Was a very famous person. He's approaching 90, if not 90 now, not in good health. After his time at Berkeley, he then was director of the NASA Ames Research Center. He became then the Secretary of the Air Force. He then became the Undersecretary of Defense, and then was the Chancellor of the University of Texas system. What we call the president of the system, they call the chancellor. So their version of Janet Napolitano was Hans Mark up until a few years ago, up until he was 85, still teaching, a real man of history. He was still doing theoretical work and experimental work. And he was very much in evidence around the department up until a few years ago, and has been very generous with the department. Cheryl Hirani, in a few lectures, formerly Sandia, now Lawrence Livermore National Lab, will give a little more of a description of the modern, the US triad today. As we have mentioned many times, the triad being land-based intercontinental ballistic missiles, submarine-based ballistic missiles. There are gravity bombs or air-delivered bombs, and then there are cruise missiles as well, usually air-dropped cruise missiles. The designations, the gravity bombs are B, B-61, B-83. There are the different mods, and then the carriers, the platforms as well. The submarine launch ballistic missiles, the W-76 and the W-88, a very, very small, very lightweight, high yield weight, modernized design. And then W-87, W-78. The numbers, you might have guessed, actually correlate approximately when these things came online. And this actually shows, even this slide I think is a bit outdated already. We've now come down to a more simplified base of, I think, sort of, depending on how you count, 7 weapon systems, and who the lead lab was for that weapon system. All of them, of course, Sandia was partnered with either Los Alamos or Livermore in terms of the purely engineering components. Los Alamos has done by far the majority of them, with Livermore the minority number of them right now. And again, let me just, we will move on from here, and I'll go to the next slide deck because I think you'll be hearing more about this from Cheryl. Okay, good. So I am going to close this one and open up this one. I want to amplify a little bit more on the excellent lecture that was given to us by Scott Kemp, but which focused specifically on the physics, the technology, and the history of centrifuge technology. Centrifuge, in terms of uranium separation, is just one of 4 methodologies, but as he pointed out, is really the tool of choice today. And I think he compellingly made the case that it does not take a state of great sophistication, but with proper materials and some good engineering, can get online with a very credible enrichment program in a very time economical way. And I think you remember his chart that some countries were able to, from a sort of a dead start, able to have a centrifuge farm online with a meaningful number of separable weapons units, SWUs, in as little as 2 years, and even on the high side, generally not taking more than 6 years to have a centrifuge capability up and running, capable of supporting a nuclear weapons program. Just a few things here. I may have mentioned this before, but something fun. I hope you get a chance to see this someday. The Nuclear Engineering Department is actually in possession of the world's first macroscopic sample of plutonium-239 that was separated, chemically separated at the University of Chicago in 1942. The actual plutonium was made at the cyclotrons, both in Berkeley and in Washington University in St. Louis, and with the irradiating effectively ton-type quantities of uranium, this is plutonium, and ton scale, the ton scale amounts of uranium-238, and then bringing it to Chicago, and with the world's best chemists at that time, in literally just a year, invented whole cloth the separation technology for an element, a chemical element that the world had never seen. These were really giants of chemistry. In the Smithsonian in Washington, D.C., you'll see a little aluminum foil that has embedded in it the world's first atoms of plutonium-239, but we actually came to possess a little shoebox, or not a shoebox, a little cigar box of that was sitting down in the hazardous materials facility on campus. Phil Broughton, one of the EH&S rad techs, contacted us and said, before we ship this to Idaho and bury it, we thought you ought to know about this. Would you be interested that the university maintain it? We think it is the provenance is of it, that this is, in fact, Seaborg's first plutonium. And in fact, we looked at the documentation in there. There was a little plastic cube with a reticule. You could see this very, very thin platinum wire there with a little, a small little flattened part on the end. And there was something about the size under the reticule, you could see about the size of a flake of pepper. And we had some meetings to determine what should be done, how we would go about determining the, in a certain sense, the authenticity of it. And Professor Rick Norman and a student and a research associate of his decided that just on passive gamma and X-ray measurements, they could determine whether this was, in fact, Seaborg's original plutonium. And indeed, the documentation in the box purported that this was 2.7 micrograms of plutonium-239. And the measurements that were done by Norman and his students came up with 2.4 plus or minus 0.3 micrograms. Everything jived with what it was expected to be. And we're now going to be putting this up in a little sort of a small museum that I think eventually is going to be constructed inside of Gilman Hall. Okay, we've talked about all these things here. Well, one thing we didn't talk about in terms of separation technology, and that is, where does uranium come from? Well, this country has a large repository of known recoverable resources of uranium, but we're far away from being the largest. Australia is about 1.7 million tons of uranium that are easily recoverable. Kazakhstan is second. Canada and Russia are both very large, nearly 500,000 recoverable tons of uranium. South Africa is very high, Namibia and so forth. In fact, during the war, in World War II, when it was feared that the Germans were going to were going to have a rapid nuclear weapons program. In fact, that's what was known were the, in fact, the places where we knew about that had large ores of uranium was Africa, and in fact, that became a contested area. Now, you might say, well, it's in the hands of our friends, the Australians. Be a little careful there, because it's not simply an issue of who owns the thing, but who actually has, established the contracts to purchase it. Then you say, well, okay, it's not only simply owning the uranium, but then you have to produce it, process it as well. Interestingly there, although Australia by far is the largest resource, in fact, they only produce 9% here. In fact, Kazakhstan actually produces the most in terms of usable uranium. And once again, although the Kazakhs in principle are our friends, I think, again, most of the contracts have been signed with the Russians. So the whole chain of kind of ownership or the supply chain of uranium is more complex than it first looks. We talked about the four methods: gaseous diffusion, electromagnetic separation, the centrifuge, and laser isotope separation. All three of the have been used and heavily, the diffusion and separation in World War II, the laser isotope separation is a later development. I'll just give you a brief gist of how that happens. Professor Kemp gave us a wonderful technical discussion. In fact, I was surprised. I got into quite a bit more physics than I was thinking he would, both on terms of gaseous diffusion and the gas centrifuge. But in both cases, one utilizes the very, very small, sub 1% mass difference between, or approximately 1% mass difference between 235 and 238. In one case, a diffusion coefficient there. The varying as the square root of the mass as the way that one could stage by stage develop a very slight preference for passing the 235, which would have a slightly higher velocity than the 238. Both, given that whatever particular separation technology you have, if you have a technology which gives a very slight advantage to the 235 or the 238, one then gets into a very interesting mathematics problem, kind of an operations research problem, which is basically called Cascade theory. And what is very plain is that one can actually then cascade several separation stages in a row, such that one gets powers of the 1 plus epsilon, 1 plus epsilon, 1 plus epsilon squared, 1 plus epsilon cubed. But of course, what one doesn't do is simply push in an immense amount of fuel stock here, F being fuel or feed, P being product, and then simply throw away irrecoverably the waste, because it's obvious that the waste itself contains almost as much uranium-235 as what went in, and therefore one can take this waste stream and then feed it back upstream again, so it gets a second, third, fourth, fifth chance to harvest out the isotope of interest. So think recycling. And
we have a question in chat.
Oh, I wasn't looking at the chat box. I should probably keep the chat box open here. Where's the question?
James Parks asked, how do countries buy uranium? For instance, why would a country sell to North Korea if they know that most countries do not support their program?
That is an interesting question. And I think if Professor Nacht is on, I think he can probably give that. So why would a country sell to a proliferant country, in other words? Was that the essence of the question?
I think so.
Okay. James was okay. Can you can take yourself off mute and talk here if you wish.
Yeah, that's exactly what I intended.
Okay. Well, I think people will encourage or supply proliferants for two reasons. One is that they are unprincipled and need cash. And the other is that they may be kind of, political kind of fellow travelers who wish to give the U.S. and the Western, alliance political problems like that, and both are irresponsible. But if Professor Nacht is on the line, he may want to unmute and give some history here.
Okay, can you hear me?
Yes.
Okay, great. So there have been a few countries that historically have been connected to the North Korean nuclear program. One includes China, and China has had a sort of complex and subtle relationship with North Korea because they want to maintain decent relations with the US, but at the same time, they've been the principal supplier of food and fuel for North Korea. And they probably have had some role in the assistance of the North Korean nuclear program. Russia also at one point was involved with the North Korean program. I don't know, Mansuk, you may know, but I don't think that they're involved now.
Russian guys?
Russia. You
unmuted?
Unmuted?
If I unmute, there will be some howling problems.
Oh, okay, okay.
So after the collapse of the Soviet Union, Russian scientists, some of
Can they hear you?
Yeah.
Yes.
Yeah, we can hear Mansuk.
Some of Russian former Soviet Union scientists went to North Korea to help them to build like enrichment facilities and reproduction facilities. But this is not official. Probably this is rumor. I heard that all Russian scientists went back to Russia.
Yeah, I think that's right. In addition, Iran has had good relationships with North Korea. And Syria, of course, acquired a nuclear reactor from North Korea, which was bombed by the Israelis. So basically, countries have been somewhat isolated from the international community, or those that have their own bilateral interests in improving relations with North Korea have done business with them.
I have one more comment. So in terms of uranium export and import with regard to North Korea has its own uranium mine and uranium fabrication facilities. So they, North Korea makes its own yellow cake, UO2, and a UF6. So they could, enrich their uranium by themselves. So North Korea has a whole, fuel cycle facilities in the state. So that North Korea doesn't need to get doesn't need to be provided with uranium materials from outside.
Right. Does that answer James's question?
That does. Thank you so much.
Okay.
All right. So here is, let me get back to the issue of a cascade, and I'll use my cursor as a pointer. As Professor Kempt outlined, one has some latitude to how to design a cascade. One normally will feed in, one will have stages both quote unquote below, i.e. Which process tailings of lower enrichment, and then many more stages going upwards towards the product. The output goes into stage, from M goes into stage M+1, M+2, like this. Why is this doing this? Okay. However, the tailings, i.e. the waste products which come out at lower enrichment, can get fed back into the previous stage for a second try. It's an easy math problem to show that if the enrichment factor is R, and R is a number very, very, very typically very, very slightly greater than 1. Typically, as he was mentioning, in the best of cases, it might be 1.02 for a centrifuge, something like that. Then if you decide you're going to pull out the number of stages you need will be the enrichment of the product you want divided by the enrichment of the waste, at which point you're going to say, okay, tailings below this level, we're just simply going to discard and put into a tailings pile like that. And so R to the N is that ratio. The total number of stages N then, if I just invert that, is the log of that ratio divided by the log of R. And that gives rise to a very large number. As you can see, if I want weapons grade uranium, 93%, and I agree to or decide that when I have gone down from 0.7% to 0.4%, I'm not going to bother anymore adding on more stages. That gives rise to close to 4,000 stages that are required there to do the job. This is what there are different types of cascades: square cascades, symmetric cascades. In fact, a little reflection will point out that a mathematically optimized cascade will have many, many more stages lower down and relatively fewer at the higher stages of enrichment. And that's because one is dealing, when one starts with only 0.7% uranium-235 in natural uranium, in order to ultimately get out kilogram quantities for a weapon, one needs to start with ton quantities on the feedstock. But as one purifies that, more and more is in the waste stream, and therefore you're dealing with a lower, as you go up, you're dealing with a smaller inventory of feed at each stage, which is why you can deal with fewer of your separations units, whether they be gaseous diffusion or centrifuge. We'll get into the mathematics of that in just a second, or just some numbers, not real math. He mentioned that the staggering size of what was built up in World War II. Here's the K-25 plant at Oak Ridge. It's post-World War II, but it's still was from many, many years ago. It's very difficult to comprehend the scale of that photograph, but that building is more than a mile long. And this was part of an enormous complex that was built up of reactors, calutrons, gaseous diffusion plants, laboratories of scientists, at what today's cost, I think, would be many tens of billions of dollars, all done in less than 3 years. I mean, the scale of this was incomprehensible. Here's a more modern one that was the Portsmouth gaseous diffusion plant in Ohio. All the U.S. gaseous diffusion plants have now been shut down. Again, the scale of this is very difficult to comprehend. Again, that's more than a mile long. This is a very, very large plant. Let me talk a little bit about electromagnetic separation, because this comes back to a little bit of local history. We talked before about Alfred Nier, one of the premier mass spectrometrists, spectroscopists. In fact, one of the fathers of mass spectroscopy in the 20th century. There is this little evacuated semicircular tube was his first mass spectrometer, which determined the mass difference of 235 and 238, and was able to separate the two beams of 235 and 238, collect them, and then determine which was the fissionable species at the Berkeley cyclotron. And the mass of this is pretty simple. when one accelerates an ionized uranium atom, independent of its isotopic number, whether it's 235 or 238, it has the same kinetic energy, 1/2 mv squared. But if the energy is the same for the two, the one with the lower mass will have the higher momentum. Excuse me. Yes. So you actually have there the one with the higher mass has the higher momentum, and will have the larger radius of curvature, rho, in the magnetic field. And this gives rise to kind of the general principle. One accelerates, and then one momentum separates the heavy from the light species. One blocks or stops the heavy one, and then one preferentially collects the lighter one. And here is Lawrence's original conception of the Calutron. And tubuloy, of course, was the code name for uranium, the fissionable uranium in World War II. And the first test of this principle was done at the 184-inch cyclotron, which was under construction to do basic science, and then the needs of the war effort. They actually used, that's today's ALS, Advanced Light Source, is in that iconic historical building that you can see from across the bay. There's the picture at the time of the size. There's what's called the yoke, the two pole pieces of the cyclotron. And then you can see all these pretty famous people here. And if I looked in detail, there's Lawrence himself right there, and his students and his postdocs and his technical staff. And they put one of the first sections here is and tested the principle at Berkeley, and then built this in large scale at Oak Ridge. Here's what they had the alpha and the beta Calutron, Cal standing for Cal, Berkeley. And there is the semicircular shape vacuum chamber of the mass spec. And what one did then is simply build just to sort of make most efficient use of the magnetic field, one built a kind of a toroidal individual magnet coils there. So the magnetic field is now sort of perpendicular to each cross section. Each of those sections there is removable. Let me just, this is a Sujay here. Great, that was the dean, but you're so important. I'll talk with my dean later on. Okay, this was again a staggering effort here in size. This was an interesting story. Each of these sections, these little slices of that were removable, you could take the thing out, put another one in, and then harvest the uranium that had been captured in the catcher volume. They figured out the best people who had the most skill at continually adjusting the current and the voltage to optimize the needle, showing the current of the species of interest going into the catcher cup. Were these women that they hired locally in Oak Ridge, Tennessee, and they were known as the Calutron girls, and they were heroes of the war, really being able to optimize what, in fact, turned out to be not a very efficient process. It turns out that only 1/6,000th of the feedstock was usable, the uranium ended up being coated all over the inside of the machine. And after every run, they would take the stuff that was in the little catcher receptacle, have to purify it again, and then scrape the rest off, put it back into the feed because it still contained a lot of it, good uranium-235, and run it through again. It was a very messy and inefficient process. The program was $9 billion, so it was some, significant fraction of the overall cost of the bomb project, but it worked. And particularly the beta Calutron produced our usable, most of our usable uranium-235. And as I mentioned last time, somewhat amusing story, they signed an invoice basically taking over every last ounce of silver from Fort Knox, making it into high conductivity wire. And at the end of the war, they took the coils, melted them down, and then returned every last ounce of silver to Fort Knox. So that was the one thing that was done at high efficiency in this program. Interestingly, you might say, if Scott Kemp was right, and that gas centrifuges are the way to go, basically you could go into a student shop and with sufficient care produce a small centrifuge that would give you a very high purification factor. You might say, why were we surprised at the end of Gulf War I, after we had pushed the Iraqis out of Kuwait and back into their own border? Why were we surprised when about their program? And my old boss at Livermore, Jay Davis, who was the division leader of experimental physics at the time, and later on was drafted into or volunteered and became part of what was called UNSCOM Team 4, the United Nations Special Commission, which went in after the war, after the Iraqis had been defeated, to investigate reports that they were operating a covert nuclear weapons program, which they had denied up until that time. But of course, afterwards, they got some people to talk, and some of their scientists actually showed them places where their weapons establishment had been. In their haste in the later days of the war, a lot of materials and documents and equipment was scattered, destroyed, driven away. And he had one of the most interesting times of his life there, doing what he called his Indiana Jones routine out there with the UNSCOM Team 4. They were, for a while, I think for 4 days, they were basically confined by the Revolutionary Guard to a parking lot. They were not allowed to leave, but they did have these cell phones that would communicate directly with US satellites, and were able to talk with the US government back here, State Department and DOD. They were able to spot convoys of trucks driving away, were able to give pursuit and actually find them taking away components of their program, and then discovered a Calutron system, electromagnetic separation system, which had been buried. And what I think surprised people why they did not know about this program is that we were perhaps expecting to look for evidence and intelligence over the years about a centrifuge program, but very cleverly, the Iraqis had done their separation by this old technology of electromagnetic separation, and they had evaded detection because they had buried the power lines. And the one thing you would look for is a signature by national technical means, i.e. spy satellites, would be lots and lots and lots, humongous amounts of electric power going out into the desert for no purpose. And you would say, aha, they're running a covert separation program out there. Well, the Iraqis had buried the power lines, so our satellites never saw it. And Jay's assessment of what they did is that this was an extremely technically sophisticated program. He said it was better than what we did in World War II in terms of the Calutron technology. And his story and his photograph ended up on the cover of Physics Today from 30 years ago or so about the, his exciting days in Iraq chasing down and uncovering the Iraqi nuclear weapons program. There's one of the transformer buildings at Tarmiya. And there was a photograph they took of some Iraqi trucks racing away, trying to take away components from their plant to avoid the whole thing being uncovered. But again, they had scientists who talked and many, huge reams of documents which fell into our hands as well. I want to say too much here because this was covered by Scott. There was the American Centrifuge Project, Piketown, Ohio. Again, you see these farms are truly massive. And just some numbers here. People often wonder, we talk about natural uranium being 0.7%. We talk about low enriched uranium, LEU, being less than 20, and high enriched uranium being greater than 20, bomb grade being 90%. And I think for kind of the person in the street, they often, they read, in the newspaper about, Iran, getting their toes up to the line of 20%, low enriched uranium. Of course, they've gone beyond that now. But you say, what's special about that and why is 20% such a significant milestone, and why is that considered so dangerous from a proliferation point of view when you really need 90% enriched uranium to make a practical bomb? And this is really an issue of the breakout time. And here's the numbers on two view graphs. And what I call just the surprising logic or the surprising math of enrichment. So here is a somewhat of an idealized enrichment cascade. You have, in fact, here's the feed at at the stage that you feed in of 0.7%, 0.72%. So that's natural uranium. You have what comes out called the head enrichment, and then the tail enrichment is what is left over. This, you can see, is almost unrealistic. This is sort of like about a 15% enrichment per 1.15 enrichment per stage. So this is something I think is quite unrealistic, but I think that this is just a mathematical toy just to show you the numbers of this. You, of course, have to have some stages below there, because if you then want to go back and take your tail stream and give it a second pass, third pass, fourth pass, give it as many opportunities as you can to harvest out its uranium and then ultimately throw the stuff away at some lower enrichment. You have, so if you feed in at stage 3 and you have stage 1, stage 2, to go from 7.2% up to 20%, here you can see at the bottom of the page, takes roughly 20 stages. If I add up the number of centrifuges here, this turns out to be 283. Now, to go from 20%, 21%, to up to here we are at 94%, only takes an additional 23. And the reason is, as you become more and more enriched, your total inventory of the feed for the next stage is going down, 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 down. So the number of centrifuges at any particular stage is a very, very small number. It goes 2, 2, and then 1, 1, 1, 1, 1, 1, 1, all the way down. So 306 total. It takes 90% of those to get up to 20%, but only 10% to go from there, from 20% to 90%. And that's why when this boundary line, this arbitrary boundary line between what we call LEU and HEU is really quite scary, because that means to say uranium at that level takes a very small sprint to get up to making your first weapon, something that is then you're really measuring in timescales of weeks, the breakout time. Final point here is again, a laser isotope separation, which I don't know the detailed history of. I do believe the patents date from the 1960s. The laser, I think the principle of the laser, of course, came from the maser, invented by Charles Townes, professor of Berkeley, Nobel laureate. But the microwave amplified stimulated emission, and then the laser, meaning light amplified stimulated emission. Once the laser invented, even before it was invented, people envisioned all kinds of incredible applications for it, which at the time may have seemed utterly fantastic, but of course have all been borne out and even more, what the marvels of the laser has done. But very quickly it was figured out that there was a very high-tech and very clever way of separating isotopes, lithium-6, lithium-7, 235, uranium-235, uranium-238, anything you want, due to the fact that from an atomic physics point of view, the atomic spectral lines have a very, very small mass shift. In other words, the same atomic spectral lines in 235 will be very slightly shifted and in fact split from those, 235 would be shifted and even split from those in 238. But given that they're at different frequencies, one can see the game one wants to do. In short, one wants to take a laser that would bring you from one or more lasers that would excite you from a particular atomic physics line in uranium-235 up to, preferentially from that one up to its separation energy and to knock an electron off. So one can preferentially excite and ionize 235, leaving uranium neutral. And how this all works is that one is going to take a beam of sort of a vaporized beam of neutral species, both 235 and 238. And one will then tune the laser beam to selectively promote and ionize the charge of interest, or the species of interest. Where's my cursor here? Once ionized, of course, in an electric field, they will be attracted to a collector of the product, whereas the 238, which has not been excited and ionized, would go into the tailings collector. So here it is in kind of a cartoon form, schematized form. The uranium flow comes in. 238 is unaffected to 235 because you've tuned to this line, which gets you up to another level, which goes you up to excitation state, or to the ionization state. One collects on a metal plate, at some point takes it off, scrapes off the product of interest, I believe that the patent holder on this in the 1960s is an Israeli. I think that the original patent is an Israeli patent on it. This became a very big program when I was there called AVLIS, the Atomic Vapor and Laser Isotope Separation Program. It used these copper vapor lasers, which were then frequency multiplied, and they converted the green light into red-orange light, and that were only absorbed by 235. Ed Moses was the head of the project, who later on led also the massive National Ignition Facility as well. It actually worked. It ultimately was sold to the U.S. Enrichment Corporation, one of these interesting constructs, one of these federally owned corporations. But ultimately it was shut down. I think they realized that the U.S. had, or the world had quite enough uranium fuel, and this was not needed overall at a pretty significant loss. But it did, from a technical point of view, produce ton-scale quantities. Interestingly, although I'm not aware that this is being used by to any large extent by countries these days, it does not take a terribly, nowadays with laser technology being what it is, does not take a hugely technically advanced nation to carry this out. Even a moderately technically advanced country could put together a laser isotope separation program. So it is something worth worrying about from a proliferation point of view. Interestingly, it did have a spin-off. Clara Max, professor at UC Santa Cruz now, she was at Livermore at the time, and Will Happer, a very famous physicist at Princeton. He had been the White House science advisor under Bill Clinton. He was ultimately booted out by Al Gore for actually wanting to ask scientific questions about global warming. I mean, sincere questions there that I think the vice president had no humor for, but they actually were working, I think, both for the Jasons at the time, this body of experts that advises the government on national security affairs, very top-level scientists, and they conceived of a way of using a laser to ionize the sodium. There's a very weak sodium layer at something like 90 kilometers above the Earth due to meteorites coming in, vaporizing, leaving lots of elements up there. They realized they could use a laser to fluoresce the sodium in the upper ionosphere, and therefore produce an artificial star. And that star would, obviously jiggle around because of the atmospheric turbulence. You could actually use the position of that star to correct real time the optics of a telescope to take out the effects of atmospheric turbulence and get much clearer pictures from the Earth. And this was, of course, has been a huge contribution to astronomy. And she's a member of the National Academy and director of the Keck observatories of the University of California. Let's see. There's only 5 minutes left to go. I was going to do a third slide deck, which is on the weapons effects. But I think I am going to get an option to do another half lecture sometime, I think, after the break. And so I think I'm going to hold off on this. This will be approximately half of a 90-minute class. On Wednesday, we will have George Moore from the Middlebury Institute of International Studies in Monterey. And he is actually going to give us a lecture as well. And so Professor Nacht has arranged for Dr. Moore to be with us. He's been graciously given lectures in our class before. And Michael, I didn't know if you wanted to make any a little bit of a preview or announcement of what we're going to hear from Dr. Moore.
Yes, can you hear me okay?
Yep.
So Dr. Moore has an amazing background. I'll give a fuller introduction of him on Wednesday. But among other things, he was a key figure at in the Safeguards Division of the International Atomic Energy Agency for a number of years. So he's very knowledgeable about the role of the IEA in determining whether countries that have signed the NPT have complied with its terms. And he's going to discuss how the IAE monitors compliance of countries with the NPT. That's a short version. But he's a very interesting man with lots of different experiences, as I'll explain on Wednesday.
Good. I think this was my first experience giving a full Zoom lecture under my own soloing, actually controlling the Wurlitzer myself and getting the thing on shared screen. And I think it worked well. I'm glad you were able to hear and ask questions. That's what the drill will be for the remainder of the semester. And then, of course, we have a break coming up next week. And Austin, did you want to say anything about when have the exams been returned?
No.
Not yet. Mansuk, you might have more to say on that than I do.
So I almost finished the policy section dating. So probably I'm gonna send it out to professors later today, and students will get their grades probably this Wednesday or next week.
Good. All I would say is we did grade promptly the technical part, and I think we were all extremely pleased that the class has really assimilated the basic material in a very good way. So I think we're very, very happy with your progress, and we'll get these exams back. And then remind me, Austin, the second homework was collected, was it this Wednesday or last Wednesday?
It will be collected this Wednesday, yes, at midnight.
At midnight, oh dear, okay, good. Okay, everyone be well. And if there are no further questions, we'll let you go.
Thank you,
Thanks.
Carl. Great job.
Bye-bye.
Thanks,
Bye-bye.
Carl.
Okay.
Thanks, Carl.
Take care. Let's see. I'm trying to get rid of this thing here. All right.